Okay, in any engineering project, we generally assume that the stresses are within the elastic limit and use the theory of elasticity you learned in strength of materials. So we can calculate the deformations in 3 directions. For doing all these things, we need the modulus of elasticity and also Poisson's ratio. The modulus of elasticity can be obtained from a axial strain versus deviator stress curve, pretty much the same way as you did in your strength of materials. If we have a straight line portion here, up to the proportional limit, we can take the slope of that line as the modulus of elasticity. But most of the times in soil testing, we get this curve right from the beginning, so there is not really any straight line portion. So that's one reason we want to use other method. When we do this consolidated drained test in the lab during the drained shearing portion, so here we keep these walls open. We keep these walls open, so water comes out of the soil sample, allowing us to measure the volume change of the sample. We also measure the axial strain, and we know the stresses in the 3 directions, sigma 3, sigma 2 equal cell pressure applied by this cell pressure control, and sigma 1 is the cell pressure plus axial load divided by the cross-sectional area, the deviator stress. So it's not too difficult, but it requires some patience. Most of the textbooks do not explain that, but I have one example to give you here, similar to the quiz problem you have. So let us say we have a soil sample and we are doing CD test on the CD Triaxial shear test, which is the slow test, drained shearing, slow drained shearing, that gives us that is going on under sigma 1 equals 170 kPa, sigma 3 100 kPa, which of course is equal to sigma 2 as well, and they are also equal to the effective stresses because there is no pore water pressure. That means we have a sample like this, and let us say the sample is 35 millimeters diameter, and this length is originally 70 millimeters, and we are applying sigma 1 this way, and sigma 2, sigma 3 applied in the horizontal direction. So this sample becomes shorter and it bulges actually. Let us say it becomes 66.5 millimeters in length. So it becomes something like this. These end caps do not allow it to change the dimension there, so it becomes something like this. It's become shorter, bulged a little bit. Overall, the volume decreases. This is 66.5 5 millimeters, and that we can find out. And the change in volume delta V is V minus V prime. This is that is original volume minus final volume, which is also the water volume drained, volume of water drained. Let us say in this example, this is 3.72 milliliters. Sometimes we use the milliliter, that means this is 3.72 centimeter cube, and if you can convert that millimeter cube, this is 3720 millimeter cube. That much water came out. That means this red volume is smaller than the brown volume. Brown volume is the original volume, and this is the reduced volume. That happened under these stresses, sigma 1 being 170 kPa and sigma 3 being 100 kPa. In your strength of materials class, if we have three-dimensional stresses, sigma 1, sigma 2, sigma 3 acting on an element, you might have calculated these strains. Epsilon 1 equals sigma 1 minus Poisson's ratio times sigma 2 plus sigma 3 divided by the modulus of elasticity. In the same way, epsilon 2, epsilon 3, you might have calculated here sigma 2 for epsilon 2 minus mu times sigma 1 plus sigma 3 divided by E, and here this is sigma 3 minus mu times sigma 1 plus sigma 2 divided by Young's modulus. The material has the same modulus of elasticity and same Poisson's ratio, but sigma 1, sigma 2, sigma 3 being three stresses, epsilon 1, 2, 3 are the strains in those directions. So here, essentially, we don't have to bother about this because these two are equal in this case. Equal, and we know this epsilon 1 because we know this changed length, so that we can calculate accurately from the measurements. This is 70 millimeters minus 66.5 millimeters divided by 70 millimeters. This is 0.05, 3.5 millimeters reduced out of 70, 1/20th. We don't know epsilon 2 or 3, even though we know that they are equal, but we know the stress conditions, we know so we can make use of the stress conditions and write an equation for epsilon 3, and epsilon 3 should be 100 kPa. As I will write once more, sigma 3 minus mu times sigma 1 plus sigma 2. Let us equate it with sigma 3. As I said, these two are equal by E. That means this is 100 kPa minus Poisson's ratio times 170 kPa plus again 100 kPa divided by the modulus of elasticity. So this is one equation we have, and we have the volume change known to us. So the original volume V is pi over 4 d square L, which we can calculate is pi over 4 35 millimeters square times 70 millimeters based on the original dimensions of the sample. This is 67356 millimeter cube. I will not go for any decimal because this is such a huge number, 67,000. There is no need for that. We can calculate V prime because we know this. We can say that final volume V prime is V minus delta V. That means from this 67,356, if we subtract this, we get the final volume, which is this times the other shape. So what we are trying to do is we are trying to get the average diameter after it bulged like this. So this is 67,356 millimeter cube minus what is this 3720 millimeter cube is 63,636 millimeter cube. So this is pi over 4 d prime square times L prime. We know this L prime as 66.5 millimeters. This is the final length. And the final diameter is this. This is average, you can say, because the sample, because it is attached to the bottom cap and top cap, it bulges like that. So we can use this final volume, this length, to get this d prime, and that d prime we can use it to put in this equation, calculate this epsilon 3, because we know the original diameter 35 millimeters, and then solve for E and this, because we have epsilon 1. Also we can write one more equation. So I will erase a little bit here and write that. So let us first calculate d prime. Pi over 4 d prime square times 66.5 millimeters is this 63,636 millimeter cube. So rearranging, you can say d prime is 4 times 636 millimeter cube divided by pi 66.5 millimeters. This square root, because this is d square, we taking that, we can find the change diameter is 34.904 millimeters. This is the final diameter. From 35 millimeter to 34.95, That means epsilon 3 also that is 35 millimeters minus 34.904 millimeters divided by 35 millimeters. This is the reduction in the diameter, the original diameter. So this is approximately 0.00274, which is also epsilon 2 because those three are equal. So epsilon 3 is this and this is this, so we can let us equate these two things. So epsilon 3 is this one. Okay. So now we can use this equation and also write this epsilon 1 equation in terms of the original stresses applied. So that means let us write that also here. This epsilon 1, as we have calculated, is equal to sigma 1 minus mu sigma 2 plus sigma 3, which are equal, divided by E. That means this is 170 kPa minus Poisson's ratio times 100 kPa plus 100 kPa divided by E. So this is one equation. In this equation we know the value, and in this equation also we know the value. In both these equations we have both Poisson's ratio and modulus of elasticity, two equations, two unknowns. You should be able to solve these equations. I will write them once more here, say in red color. Say for example, multiplying this with this, 0.00274 equals 100 kPa plus, not plus, minus, minus, this is 170 plus 100, 270, mu times 270 kPa. This is one equation, and from this what you get is 0.05 E. If you want, let us put some more zeros, but I don't think zeros are required. Let us stop there. 0.5 E, I'm just multiplying these two things, equals 170 kPa minus mu times 200 kPa. This is equation 2. With all the math knowledge you have, you can solve these two things and get the E and Poisson's ratio values. So if you take time to solve these things, you will be getting E as 2000 kPa and Poisson's ratio as 0.35. Poisson's ratio is typically between 0.2 and 0.5, but getting it as confidently as we can, that can result in very good results. That can give us very good results. You should have seen these values just given to you in the Strength of Materials textbook. It's not so difficult to get this Poisson's ratio for steel and other materials, but for soil it takes quite a bit of effort, but we can do that. Thank you.